So I'm going to speak about the Hurwitz existence problem for branch covers between surfaces. I'm afraid this will not be very quantum, and it's also not terribly new. I mean, most of it, so we'll present a survey of some results obtained over the years, and then some recent stuff and perspectives. So let me remind you what a branch cover is. So you take two closed surfaces, say orientable, then I will quickly mention the non-orientable case. So a branch cover is a map between sigma twiddle and sigma that's locally modeled only in a topological sense over z goes to z to the power k. And so k is an integer, and if k is larger than 1, you say 0 in the target C is a branching point, and you call k the local degree at this branching point. So easy fact is that branching points are isolated, so there's a finite number of them, say n, and that if you remove the branching points and all their pre-images, you of course get a genuine cover of some degree d. Maybe I didn't say surfaces are connected, they are connected. And the local degrees over the jth branching point gives you a partition pi j of d, which means a bunch of integers unordered but with repetitions that sum up to give d. And now, since removing the branching point you get a genuine cover, you know all the characteristic is multiplicative under genuine covers. So you remove the n branching points downstairs, you remove all their pre-images, and there's as many as the sum of the lengths of the various partitions by I, pi 1, pi n, and then, so all the characteristics should be multiplicative. So chi of sigma twiddle minus the total length of the partitions equals d times chi of sigma downstairs minus number of branching points. And this is the Riemann-Hurwitz condition. So this is a necessary condition. Now, the Hurwitz existence problem, which is about a century old but not completely solved yet, asks in my language, I use this symbol to say, suppose you have all the above. So you have two surfaces, sigma twiddle and sigma, d, some number n, some number, n partitions of d, and satisfy Riemann-Hurwitz. The question is, does it come from a map? So problem, is every candidate cover? So this dashed arrow for me means all the combinatorics is okay, but I don't know if there is a map. And this is a candidate. And the question is it always realizable by some f? And the answer is no in general, but yes in many cases. And there are some exceptions, no. So the cases where it's okay but not realizable, I call it exceptional. I just want to quickly mention in passing that if you want to play the non-orientable version of this game, then there are some obvious conditions. So if you want to cover, so non-orientable will never cover orientable, and if orientable covers non-orientable degrees even, and easy things, but there's one more. So there's a congruence that does not follow from the other conditions. N times d plus the total length should be even. And I just want to very quickly explain why by an example. So if you want to cover the projective plane, say with only one branching point and one partition consisting of d only, so a projective plane is a disk union a Möbius strip. So if you want to cover this disk by z go over z to dd, you want something here over the Möbius strip. You will have a cover, genuine cover of the Möbius strip, but the boundary has to be connected because there's only one disk here. So it has to be a Möbius strip as well, so the degree must be odd. And then n times d plus the total length, which is just 1, should be even. So in the non-orientable case, there is also this non-obvious condition. So how do you face, this is very old stuff, and then I come to newer stuff. So how do you face this problem? One way is to use the monodromy and permutation. So there's this classical fact, easy, that a candidate is realizable if and only if you can represent the fundamental group of the surface minus n disks, remember n is the number of branching points, in the permutation group of permutations over these symbols, in such a way that the image of rho is transitive, which corresponds to the fact that the cover will be connected, and the cytostructure of the image on the row of the boundary of the jth removed disk is pi j. So it's the product of cycles of length corresponding to the length of the partition of D over the jth point. So this is an if and only if that's very easy. Now note that the fundamental group of sigma minus n disks in the orientable case is the product of it's generated by presentation of always one relator, 2g plus n letters, orientable case, and these one non-relation, or k letters and plus n and this relation. So since the condition you must satisfy about rho in order to get the desired cover only regards the image on the row of the boundary of pi j, you see the boundary of delta j. The boundaries of the delta j's always appear in these relations, but there's only one. So in some sense, if g is large or k is large, you have a bigger group and basically the same condition to satisfy. So you have more flexibility. And this actually is the case. So one of the breakthroughs in this theory was a paper of the, I think, mid-70s by Edmonds, Kulkarni, and Stone that proved precisely this. So if sigma is orientable and non-positive Euler characteristic, so G is at least 1, then the cover is realizable. And same if it downstairs is non-orientable, and the case where it's projective plane and non-orientable upstairs, again, is always realizable. So you see, from these three cases, what is left is only the case where sigma is a projective plane or two-sphere. But for sigma projective plane, and in the projective plane case, sigma trido orientable. But in this last case, so here there are exceptions, but this problem is equivalent to, of course, I mean, if you have something orientable covering P2, it will factor through S2, so your problem becomes a problem of the sphere. So for this reason, I mean, the problem is only open for sigma equal to the two-sphere. So in this case, there are exceptions, and I will give 4 different proofs of these facts. Actually, I know 5, but the 5th one is more involved, and I will not give it. And they're all quite elementary, but it's interesting to see as examples of the different ways you can use to approach the problem. So first proof is this example. This is the smallest exception. So you want to construct a branch cover between the sphere and itself of degree 4 with 2 branching points lifting to having double branching, and the third branching point being regularly covered by one point and triply covered by the other one. And this is impossible. And one way to see this is, so if you want to use the permutations approach, you need to have 3, it's the product of 3 elements equals to 1, because the pi 1 of S2 minus 3 point is just the product of 3 elements is generated by 3 elements with product equal to 1. And then, so if you want the one branching point to have local degrees over it 2, 2, you have to have product of 2 transpositions, and the other one, again, the product of 2 transpositions, up to renumbering 1 to D, it's 1, 2, 3, 4, and it's actually very easy to see that the product of these 2 things is either the identity or, again, 2, 2. It's never 1, 3. So this 1, 3 you cannot realize. So another technique that is quite useful to face the problem is the descent of Grothendieck. And so for this case, I will restrict to, again, sigma, the 2-sphere, as I said before, and only 3 branching points. And I will explain the reason for this later. So the sphere, you can view it as being obtained from a segment with its 2 ends being white and a black vertex, and a disk glued to it along its 2 edges, both edges. And so suppose you have a cover realizing some combinatorial candidate. So you have a map F, and so without loss of generality, you can assume that the segment, you can place your segment so that the first end will correspond to the branching point with partition pi 1 of D, the black vertex branching point with partition pi 2 of D, and then the third branching point with partition pi 3 will be the center of the complementary disk. So if F exists, you can lift this segment, and you will get a graph in the candidate covering surface, so in the covering surface sigma twiddle, and so it's easy to see. It's going to be a bipartite graph. Every edge joins black to white, and so the valences of the vertices are just, so this is valence 5. It means that one element of the partition pi 1, say d1i, so notation is pi j is dji, as ai varies. It's the length of it's one of the elements of the partition. So the various valences over the white vertices are going to be the elements of the first partition. Black vertices valences are length of the members of the second partition. And then the complement is going to be a union of disks, because each disk is covered by a disk. Not embedded, of course, but it's going to be a disk. And the total number of both black and white vertices of each disk is going to be one of the elements of the third partition. And the other way around. So if you have a descendant found with all these valences and length of the complementary regions, you also have a map F. And so using this second proof of the exceptionality of these 2, 2, 2, 2, 3, 1, so suppose you have a 4-to-1 cover of the sphere onto the sphere with two partitions 2, 2, and the third one you don't know. Then if you lift this segment, so if you lift a valence 1 vertex in a twofold way, it will become valence 2, so it's not a vertex anymore. So basically this will lift to a curve, just a curve. And if you have a curve in the two-sphere, the complement is a union of two disks, and both these disks have 2 black and 2 white vertices. So you only get third partition equal to 2, 2, 2, 2, not 3, 1. Now, using this technique of descendant fun with Katia Pervova some years ago, we have faced some cases. And so this is some examples of things we have proved. So we have concentration on cases where the descendant fun you can figure out quite easily what it is, but still, you get interesting exceptions that were not known before. So if you want to cover the sphere by the torus with an even degree branch cover with partitions 2, 2, 2, and then 5, 3, 2, 2, 2, and then some other one, this is going to be always realizable except if the third partition is of the form KK. So this is an exception. And similarly, if you want to cover the two-sphere by the two-sphere even degree partition 2, 2, 2, 5, 3, etc., and third partition, then again we know exactly when this is exceptional. So if it's exceptional if pi 3 is AABB or 3A AAA. And another theorem that is quite useful to understand some exceptions. So I should add that there was a Chinese guy, Zheng, who tabulated all exceptions up to degree 21 by computer, and there's many of them. And so this is an easy criterion that's actually quite useful in understanding some of these exceptions. So it says that if you have a branch cover, a candidate that is actually realizable, and there exists an integer, of course larger than 1, I didn't write, that divides all the members of the first two partitions, then the members of the subsequent partition should be not too big. So they should all be less than d over k. Yeah?
Write down a partition like which satisfies all criteria,
Yeah. No, it's quite uncommon. Exceptions are quite uncommon. Yeah. And I will show a theorem that gives an example of that very well. So I spoke of techniques, and then I will switch to say, I mean, since it seems difficult to understand the general pattern, maybe you can try to understand special types of partitions. So one case that was studied is the case where one of the partition is small. So first, it's an old result of René Thom that if one of the partition is D only, then it's always realizable. And so if you think in the case where sigma trido is the two-sphere, and so these basically mean that you're thinking about a polynomial, because it's a map. So a map from the sphere to the sphere with degree, with branch, one point with branch in D means infinity is, if the degree is D, infinity is covered by infinity with D to 1 times. So this is a case of polynomials. So I didn't mention that all I'm speaking about is, I described topologically, but if something exists topologically, then it also exists in terms of Riemann surfaces and rational function between Riemann surfaces. But that's, I mean, sophisticated, and I will want to speak about topology. Another case with short partitions was the D-1,1 case, and this was classified by Edmonds, Kulkarni, and Stong by permutations. And then the case D-2,2 we did with Pernova with the restriction that there should only be 3 partitions. And then more generally, the D-A case was done by Pakovic about the same time with a different restriction. So he considered any number of branching points, but only the sphere upstairs. And so what we did, this we did by a technique that was borrowed by someone who's named Baransky. It's called checkerboard graphs that was initially done from between S2 and S2, and we extended to any sigma trido. Whereas Pakovic used an extension of the descendant fund that he called constellations, but it's quite straightforward extension. Another technique that that we have used with some success is the idea that, so in some cases, if you have a combinatorial data, you can prove that if it is realizable, then it will be realizable in a composite fashion. So it will be the composition of 2 subsequent branch covers. Or the other way around, you can show that some branch covers are realizable because you can exhibit two branch covers whose composition gives the desired combinatorial data. So 2 examples of things we have proved using this idea is that if you have an even degree branch cover between the sphere and itself, and the members of the first 2 partitions of the integer of the degree 2k are even, then any subsequent partition must split into 2 partitions of D halves. And this actually gives the third proof of the exceptionality of the case 2,2,2,2,3,1, because we are in this case. So even degree, first 2 partitions, all even local degrees, and then this should split into 2 partitions of 2, but that's not the case. And on the other hand, we have a positive result, namely, if that's quite special, but if you have partitions in which all the members of all 3 partitions are divisible by some odd k, then the degree is the candidate is realizable. And again, this is yes, again, thank you, yes. Now, what I mainly want to speak about is an approach using the geometry of 2 orbitals that led to some theorem that I think is rather interesting. So let me again start by easy, well-known definitions. So I will stick to orientable, locally orientable. So a 2-orbifold X is an orientable surface sigma with some, so there's a collection of integers, And this surface has a singular smooth structure, namely, so you have n special points. Away from the special points, you have just a chart, that usual smooth structure given by R2. And at the jth point, you have a smooth structure that's obtained by identifying the size of a sector of amplitude 2 pi over pj, and so you get a cone point. And this is equivalent to say that your local thing is not a disk, but it's a quotient of the disk under identifying z to z power pj. So then you have a notion of orbifold cover. That's just, so it's a map between orbifold that's locally modeled on something very easy, so just a cone point over a cone point, and it should, so the cone point upstairs should have order, which is a divisor by the order of the cone point downstairs, and this map should be commutative. So these are the local charts I described before, the quotients, and it should factor through the identity. So an orbifold cover is just this, not having this local model. And now we have a notion of orbifold Euler characteristic, which is designed to be multiplicative under cover. And so if you have a cone point of order p, you know it's p to 1 covered by a disk. So it means this vertex, which is contributes with 1 to the Euler characteristic of sigma, has to contribute 1 over p times the contribution of this point to the Euler characteristic of this disk. So it contributes with 1 over p, not with 1. So the definition of orbifold Euler characteristic of sigma p1 pn is just the Euler characteristic of sigma, in which you replace the contribution of each cone point by what it should be according to its order. So it's not 1, but 1 over pj. So you remove 1 and add 1 over pj. So this is the Euler characteristic in the orbifold sense. And now it's quite easy to see that an orbifold cover is also a branch cover, and the other way around, more or less. I mean, you should make some choices and add some combinatorial instructions, but I will not speak of that in detail. And so that's quite easy. So we saw the local model for a surface branch, for an orbifold cover is obtained by these quotients, z equivalent to z over to the p trivial, z equivalent to z over p, and you get this map by pushing down the identity. And if you identify this cone, this neighborhood of the cone point with the disk itself, you get in these coordinates, the map is just w goes to w to the p over p trivial. So it's a local model of a branch cover. And the other way around. So the other way around is if you start from a surface branch cover, you want to associate to it an orbifold in which the map is given by is an orbifold cover. So this is not really unique, but I mean there's a best way to do that, and the best way is to define Pj to be the least common multiple of the members of the jth partition, and Pji to be dj over, sorry, I made a mistake. This should have been dj, sorry. Pj, this should have been Pj, sorry. And then you get the orbifold sigma with cone orders p1, pn, and sigma trivial with cone orders pji, and you have, with these extra combinatorial instructions that I will not speak about, you have an orbifold cover. And this also works for candidates. So you can speak of a candidate orbifold cover and the associated branch cover between surfaces, and the other way around. And in this context, the Riemann-Hurwitz condition for surface branch covers exactly correspond to the multiplicativity of orbifold Euler characteristic under the cover. So you have a different language to state the problem, which in itself would not be a great advantage, but the advantage is that two orbifolds have geometry that you can employ in actually two different ways. One way is to, as a guide for producing interesting candidates that you maybe then can analyze using different means, or you can use the geometry itself to analyze realizability. And so let me tell you what's the geometry of two orbifolds. So it's a metric that's obtained by, so before I said the smooth structure is obtained by a sector of certain width 2 pi over p by identifying the edges of the sector. And now I just take the sector to be in one of the three modal geometries in dimension 2. So the two sphere, the Euclidean plane, and hyperbolic plane. So it's a metric that is obtained by taking the quotient of these three models under identification. And so I will not speak about all the details here, but so it's actually equivalent to say that you realize your orbifold X as one of the quotient of one of the three models, sphere, Euclidean plane, hyperbolic plane, under a group of a discrete group of isometries that may have fixed points, which gives rise to the cone points. And now you have the ocean of good orbifold, which is just an orbifold that's orbifold covered by a manifold. And now, so Thurston classified the geometries of the orbifold and proved that almost all of them have a geometry. And that depends, so you have an orbifold version of the Gauss-Bonnet formula, so the sign of the orbifold Euler characteristic will give you the sign of the curvature. And so in positive characteristic, you have the bad orbifolds, which are the teardrop and the football with different cone orders. And these do not have geometry, and they are the only bad ones. And then you have the spherical ones, which are the sphere with a, say, a symmetric football, and then 2, 2p, and these 2, 3, 3, 2, 3, 4, 2, 3, 5, which are actually obtained by taking the quotient of the two sphere under the orientation preserving subgroup of the symmetry group of the Platonic solids. And in zero Euler characteristic, you have the Euclidean orbifold, which are the torus, and the sphere with three cone points of orders 2, 3, 6, 2, 4, 4, or 3, 3, 3, 3, or the sphere with four cone points of order 2, 2, 2, 2. And all other orbifolds in negative Euler characteristic have a hyperbolic structure. So how do you use the geometry of orbifolds to deal with, to obtain something about branch covers? First thing is, well, one obvious thing is that good cannot cover bad, because the definition of bad is not covered by something that's a manifold. So if bad is covered by good, good is covered by manifold, then bad would not be bad. But it's also the other way around works. So lemma, bad cannot cover good. And the reason is, if you have something good that's covered by bad, you have a notion, again due to Thurston, of orbifold universal cover of X, and then as, well, universal means it will factor through anything else. And so if this is bad and this is good, you have the universal thing here, then you would have this dashed arrow, but then bad would be covered by good. So this can't happen. And this gives the fourth proof of the exceptionality of the candidate 222231, because so I said the cone orders downstairs are the least common multiples of 2, 2 you get 2, 2, 2 you get 2, and 3, 1 you get 3. And upstairs you have least common multiples divided by members of the partition. So 2 gives nothing, 2 gives nothing, and 3 gives nothing with 3, and 1 gives 3 with 1. So this is bad, this is good, so this is an exception, fourth proof. So to state what more results we proved, I need to remind you what is like Muller space of an orbifold in case of negative Euler characteristics. So this is just the space of hyperbolic structures on X. I'm not going to say how it's topologized. Modulo isometry is isotopic to the identity. And the fact is that this is a complex manifold, actually, of dimension 6G minus 1 plus 2n. And so what we proved with a former PhD student of mine, Maria Antonietta Pascali, is, so we did a complete analysis of the candidates, ex vivo, say, of the branch cover candidates associated to orbifold covers, such that first case where orbifold characteristic is non-negative, and then negative Euler characteristic downstairs, which implies also downstairs. And so downstairs, only the case where the space of deformations of the hyperbolic structure is small. So basically, the structure is rigid, which happens dimension of type Müller space equal to 0 only for the sphere with 3 branching points, with 3 compoints. And of course, in this case, 1 over P plus 1 over Q plus 1 over R should be less than 1 to be hyperbolic. And upstairs, we did up to the case where the complex dimension of the type Müller space is 0 or 1, only this case. And I want to say, I already alluded to this before, why do we restrict to the case where X is the sphere with only 3 branching points? And the reason is that there's a conjecture that was first stated, I think, in the cited paper of Edmund Kulkarni and Stone, that if the degree is a prime number, then the candidate should be realizable. And this starts leading us toward connections with arithmetic that were not quite, apparent so far. And what Edmund Kulkarni and Stone prove is that the conjecture, to prove the conjecture, you only need to do that for 3 branching points. So basically, if your goal is to prove this conjecture, you can restrict to n equal 3, and hence to the case where downstairs you have this orbifold. And so what are the results we obtain? For the case of, so there's some long list that I'm not going to give you, but I will just explain in a qualitative fashion the results. And so for the case of positive Euler characteristic, the result is very neat. So a candidate is exceptional if and only if it's of the type I told you before about. So when X is good and X fido is bad. And actually, so what you show is, first, you don't have any candidate with bad X, and then you have some, so the exceptions are 11 isolated cases that you just listed, and 1 infinite family. And so this is exceptional for that. This is an extension of what I told you before. It's even degree. Actually, it follows from what we knew before. It follows from the theorem I mentioned before, that this is exceptional if and only if A equals B. A is different from B, sorry. And then you have realizable cases, 5 isolated ones, and 2 infinite families, but again, these were known before. They follow from the result of top. So anyway, this is the main result for the positive Euler characteristic case. So I should mention that all the realizable covers you can do in a geometric fashion, but actually all the proofs can also be done in combinatorial ways that are quite easy. The proofs of existence and exceptionality. So in this case, really, it was, the geometry was kind of used to obtain a sensible list of candidates rather than really providing tools for giving the proofs. On the other hand, in the 0 Euler characteristic case, always in the orbifold sense, again we have a complete classification, and there are 14 families of realizable ones. They are all infinite families, 2 families of exceptional, and what's most interesting is that we have some 12 families in which the realizability depends on arithmetic conditions. And these are 2 of the theorems we prove. So if you want to have a cover of the sphere onto the sphere of degree congruent to 1 modulo 4 with partitions 2221, 2221, and 4441, then this is going to be realizable if and only if 4k plus 1 can be expressed as the sum of the squares of two integers. And so similar result for the case of degree 6k plus 1, partitions 2221, 3331, 6661. This is going to be realizable if and only if the degree is of the form n squared plus nn plus m squared with nn integers. And the proof of these two results really use the geometry. So you take this associated orbifold is S224, and this is also S224, and you look at the ways S224 can geometrically cover S224, and you realize, well, it takes some work to realize the degree has to be the sum of two squares, and similarly here. Now, what is interesting in this result is that, and this partially answers the question you raised before, if you take the numbers of the form congruent to 1 modulo 4 that can be expressed as the sum of two squares, then they have zero density. There are very few of them. But on the other hand, if 4k plus 1 is prime, you know that 4k plus 1 is the sum of two squares by an old theorem of Fermat. So in this infinite family, you see that there's so it's an infinite family of candidate covers that become exceptional with probability 1, because the density of those that are realizable is 0, but if the degree is prime, they are realizable. So this I view as a good supporting evidence of the conjecture. And the other case here is identical. So the density of numbers of the form n squared plus nn plus m squared in the numbers congruent to 1 modulo 6 is 0, but any of them that is a prime is n squared plus nn plus m squared by a theorem of Euler. So same qualitative conclusion. And so I repeat that this proof really used the geometry of the orbifold. Now, for the case where the orbifold Euler characteristic is negative, and I said I restrict to the case where downstairs you have a rigid hyperbolic structure, which is already enough if you want to face the conjecture of the prime degree, then, so in any fixed dimension of the Teichmüller upstairs, space upstairs, there will only exist finitely many candidates. And what we did is we listed them up to complex dimension 1 upstairs. And so it turns out that you only have 11 with complex dimension 0, and some number. You should sum up this for integers. I'm not going to do that. For complex dimension 1, and you have two types upstairs. You can have the torus with 1 cone point or the sphere with 4 cone points. And we completely analyzed those which are realizable and those which are not, using many of the techniques, combinations of the techniques that were known before. And so we found some realizable, many realizable, some exceptional. And of course, no counterexample to the conjecture, so all the exceptions were in composite degree. And I should say that many of the proofs are not really geometric. So sometimes we use the hyperbolic geometry of the would-be covered two orbifold, but not always. Often it's just easier to use other techniques. And so I will conclude with some perspectives. So one thing I'm planning to do is to analyze the case of short partitions that was left behind between the work of Pakovic and that of us, namely to analyze any partition of length 2 with any total number of branched points, but with any surface upstairs. So what the Pakovic did was only when here you have the sphere. Another thing that would be interesting to do is to really use in the hyperbolic setting the hyperbolic geometry better, namely to give really geometric proofs that would extend to higher dimension when the hyperbolic structure upstairs has a larger space of deformations. And so possibly to analyze this realizability with higher dimension of the Tacmuller space. And so this I don't think it's going to be easy, but perhaps at least if you want to stick with maximal possible genus, so you don't look at the case of a sphere with very many branching points, but high genus, so very few branching points upstairs, maybe you can classify all the examples. And actually something I've been doing these days, and this has to do with the connection with more algebraic geometric ways you have to approach the problem. So we know that these candidates, so if you take a degree that's a multiple of 3 and you want to realize partition 333, 333 and then 333, 4, 2, and you sum up and you see that this must be the torus in order to satisfy Riemann orbit, then this is not realizable, this is an exception. And so a colleague from algebraic geometry came to me and said, I can explain this by very complicated, using sophisticated tools of algebraic geometry. And now I have a proof of, a completely combinatorial proof of this fact. And so, for instance, this is delicate because if you change just a tiny bit the last partition, if you replace the final 4-2 by 5-1, or the previous 3-3 by another pair 4-2, this is realizable. So it's, it's really, and the question is now, is this part of a new pattern of candidates that you can analyze? And so these are some things I'm planning to do. Well, a bit early, but thank you for your attention.